This is session 7 of lesson 2 of Introduction to Optical Design, and we're going to continue talking a bit about conics. And conics are basically the intersection of surfaces with a right circular cone. So you can see if we cut a surface perpendicular to the base of the cone, we have our circle, and if we fully intersect the surface, so we cut through two faces of it, we have our ellipse, and now we can see our parabola and our hyperbola. The parabola, we start on one side and intersect more than halfway across, so here's the center point. The hyperbola, we cut and intersect the base of the circular cone more sharply, so within the first half of the surface. So this is graphically what our different types of conic sections look like. And we saw in the last session that there was a slight, in some instances not so slight, deviation from sphericity in the surface shape, which means we have to modify our SAG formula a little bit to take into account these conic departures. Now here is the SAG as a function of the height coordinate, and in this case y. Of course they are rotationally symmetric, so we could have been using r as well, but we're going to stick to a meridional plane, so we'll use y. And here is the definition, and this is our curvature, this is our height, this is our conic constant. And what we can do is expand this out a little bit and apply our binomial expansion. So expanding out the square root term and then plugging it in. It is of course an infinite series, but fortunately for us we don't need to worry about that many terms for at least our first order calculations. So what our SAG is simply measuring how it departs from the spherical SAG. So if we set because you'll notice the first term here is exactly equal to the term we had for our spherical surface. Now we have all these departure terms. So when we talk about the conic SAG, we're just all those additional terms are just a departure from the spherical SAG. Now if we let the conic constant be -1, so we have a parabola and we set the maximum y to be equal to the radius value, we can see that the SAG at r is simply the radius of curvature divided by 2. If we set the conic constant to 0, which takes us back to our sphere, and we again analyze it where we let the maximum y go to r, we can see that it's equal to r over 2 plus r over 8 plus r over 32 plus on into infinity, and we see that the SAG is equal to r, which is exactly what we would expect. Think of a ball lens, if you will, or half of a ball lens. Now, why do we choose to use conics? Conics have some very special properties, or in particular one very important property, in that when we've been talking about paraxial lenses in the past, I've said they're not real, they don't exist in the real world. The one exception to that is under one specific set of conditions, conics do behave ideally. This is why they're quite often used in telescope systems or other systems with reflecting components. Now, they are ideal only at this one set of conditions, and in particular we're talking about at the focus point. But here is a paraxial lens, here is a parabolic reflector, and if I have collimated light coming in, which effectively is light coming from a focus point at infinity, all of that light on axis will converge to form a perfect point image. Light coming in at any other angle or from any other object point will be aberrated, but at this one set of conditions the behavior is perfect. There is perfect geometrical imaging. And in this particular case I have an elliptical reflecting surface, and it doesn't matter which of these you take as the object point because the systems work well in reverse, but light from one focus will converge perfectly to a geometric point image at the second focus. And the focus may be real or virtual, so we will have the same behavior with hyperbolic surfaces even though the real image is not necessarily formed or is not formed by hyperbola alone. Okay. So here is an overlay of a parabolic as well as a spherical surface with the same radius of curvature, so the same focal length, and what we see is the blue rays indicate the light coming from the parabola, and it forms a perfect geometric point image at the focus. But in the case of the spherical reflector, what we see in the region around the paraxial focus is a significant amount of, in this particular case, spherical aberration. So there are distinct advantages for conic surfaces in systems that use very small fields, and by definition, telescopes fit that definition. So telescopes typically cover very, very small fields of view, and we typically have objects that are effectively point sources, stars. At a very far distance, effectively we can treat as point sources. So what will happen is when we bring the light into our optical system, we are going to end up with a relatively high image quality when we use conic type surfaces. And these are some lens designs or system designs that I've brought in from Zemax. So as you open up Zemax and go through some of the example files, you'll see, and in this particular case, this is a simulation of the Hubble Space Telescope. And you'll notice here in what's called the Lens Data Editor, both surfaces are conic. The primary mirror is almost a parabola, and the secondary mirror is an ellipsoid. In this particular case, we have an unobscured, I will fix that typo, Gregorian telescope. And in this particular case, again, the primary mirror is almost parabolic, and the secondary mirror is hyperbolic. And we're forming an image here because of the tilting of effectively the tilting of the system. Unobscured means that we don't have any of the ray bundle that's blocked out by the positioning of the other mirrors. In the case of the Hubble, we have an obscuration. The light coming in that would hit on the back of the reflector does not make it into the image, and that will affect the overall image quality, in particular the contrast. Don't worry, we will get into those concepts later. And since we're going to start on a totally new topic next, I'm going to end this session now. Thank you, and I will talk to you later.